Imagine you're building a 3D map of the world from just a sequence of 2D photos. You're not just capturing images, you're reconstructing reality. This is the heart of structure from motion, or SfM, turning flat pictures into rich, three-dimensional scenes. But how do we do it? And more importantly, how can we make it faster, more accurate, and more robust? For decades, the gold standard has been bundle adjustment, a nonlinear optimization method that simultaneously refines camera poses, 3D point positions, and intrinsic parameters. It's powerful, but it's also computationally heavy. Worse, it's sensitive to initial estimates. If your starting guess is off, the entire reconstruction can collapse into error. And with thousands of points and cameras, the problem quickly becomes intractable, what we call the curse of dimensionality. But what if we could simplify this entire process? What if we didn't need to optimize 3D points at all? That's the radical idea behind a new frontier in SfM, rotation-only imaging geometry. This isn't just a tweak, it's a paradigm shift. Instead of treating camera rotation and translation as separate, intertwined variables, this approach reveals a deep truth. Translation can be derived from rotation and the observed scene structure. That means we can eliminate translation from the optimization entirely, reducing the problem to pure rotation on the SO3 manifold. Let's unpack this. In classical two-view geometry, the essential matrix encodes the relative motion between two cameras. But it's incomplete. It ignores the chirality constraint, the fact that real-world 3D points must lie in front of both cameras. Recent work has shown that by representing 3D structure entirely through camera poses, we can define a pose-only imaging geometry, where all geometric constraints live on the pose manifold. Now here's the breakthrough. We can express the relative translation between two cameras as a function of rotation and the observed image correspondences. This is not just a mathematical curiosity, it's the foundation for a new kind of optimization. The key insight lies in a constraint known as the pose-only, PPO constraint. It arises from the geometric relationship between two views. When you project a 3D point from one camera to the other, the direction of the vector connecting the projected points is tied to the relative rotation and the direction of the translation vector. Through algebraic manipulation, we derive a symmetric real matrix, call it PS-ij, that captures the constraints on the relative translation. The solution space of the linear system, PS-ij times T-ij equals 0, tells us everything about the possible translations. And here's the astonishing part. The rank of PS-ij reveals the scene structure. If rank equals 0, the motion is pure rotation, or all points lie on the translation baseline or at infinity, what we call PRBI. If rank equals 1, all non-infinite points lie on a single plane with the cameras. This is the holoplane structure. If rank equals 2, the scene is fully general, rank regular, and translation is uniquely determined. But in the degenerate cases, holoplane or PRBI, translation isn't uniquely defined. However, here's the twist. The reprojection error used in pose-only optimization is invariant to the magnitude and sign of the translation. That means even when we can't recover the full translation, we can still compute the correct reprojection residuals, because the error depends only on the direction of the translation. So we solve for the direction of the relative translation analytically, by computing the eigenvector corresponding to the 0 eigenvalue of PS-ij. Then we use this direction to compute the pose-only reprojection error, entirely on the rotation manifold. This gives us a new framework, two-view reprojection residual on the rotation manifold, or TRRM. And because the error depends only on rotation, we can now optimize only the relative rotation, 6 degrees of freedom reduced to 3. No translation, no 3D points, no initial 3D coordinates. Just rotation. Now let's scale this up to multiple views. In multi-view SfM, we typically use rotation averaging, taking relative rotations from two-view estimates and stitching them into a global rotation. But this is fragile. Errors accumulate. Outliers ruin the result. Instead, we propose global reprojection residual on the rotation manifold, or GRRM. Here's how it works. For each 3D point, we compute its global reprojection coordinates as a weighted average of the pose-only reprojection coordinates from all views that observe it. The weights are based on the geometric consistency of the observations, specifically, the magnitude of the vector θ, which measures the angular deviation from the ideal alignment. Then, we compute the global reprojection residual as the difference between this weighted average and the actual observed image point. And because this residual is constructed from pose-only projections, it still lives entirely on the rotation manifold. The result? A global optimization problem that minimizes reprojection error, but only over rotation. No 3D points, no translation, no initial 3D structure. Just a single, clean optimization over camera rotations. And here's the real kicker. This single round of optimization achieves results comparable to 4 rounds of full bundle adjustment, the standard in platforms like OpenMVG. Let's talk performance. In simulation studies, we tested across a wide range of conditions: noise levels, number of 3D points, rotation angles, and scene depths. Our TRRM algorithm consistently outperformed state-of-the-art methods, NAIPS eigenoptimization, PA, and even nonlinear 5-point solvers. In planar scenes, where traditional methods fail, our method maintained superior accuracy. Even under high noise, it remained robust. On the real-world Stretcha dataset, known for its challenging camera poses, our two-view algorithm achieved 17% better accuracy than the second-best method. And in multi-view estimation, we saw a 27.7% improvement, with just one optimization step. But the real story is why. Traditional methods assume translation is independent. But this paper shows that translation is not a free variable. It's a consequence of rotation and scene geometry. When the scene structure is degenerate, like a plane or a line, standard methods fail. But our algorithm detects these cases beforehand, using a simple detection metric based on the eigenvalues of the observation matrix. We call these rotation singular structures. And our detector identifies them with 100% accuracy, even under 10 pixels of noise. This isn't just theory. It's a practical tool. In real datasets like Castle from Stretcha, we observed that the detection value VRS correlates strongly with the spread of feature points. Wide distribution right arrow, high VRS right arrow non-degenerate. Narrow, clustered points right arrow, low VRS right arrow singular structure. So we can prevent failure before it happens. Now let's step back. What does this mean for the future of 3D vision? It means we can now decouple 3D reconstruction from 3D point optimization. We can build accurate, efficient, and robust SfM pipelines that start with rotation estimation. No need for initial 3D structure, no need for multiple BA iterations. This opens the door to real-time, on-device SfM, to navigation in autonomous vehicles, to AR/VR systems that reconstruct environments on the fly, to robotics that map unknown spaces without prior knowledge. This is not a minor improvement. It's a fundamental rethinking of how we model visual geometry. We've shown that the origin of imaging geometry isn't the 3D point, it's the rotation. The camera's motion, encoded in rotation, carries all the information we need to reconstruct the world, provided we understand the deep mathematical structure beneath. So the next time you take a photo sequence and turn it into a 3D model, remember, the magic isn't in the points. It's in the rotation. And now we have a way to harness it, fully, cleanly, and powerfully. This is rotation-only imaging geometry, the future of 3D visual computing.